Okay, kinetics. Kinetics is how fast a reaction happens. In order for a reaction to happen, you need an effective, let's see if I can write that, collision. That means the particles actually have to run into each other, okay? So you have one particle of sodium and you have another molecule of water. In order for the sodium and the water to react, they have to collide. They have to come in contact. Hopefully that seems like common sense, okay? But you're looking for collisions. They have to collide with enough energy to overcome the activation energy, which we'll talk about on the next slide. And they have to run into each other with enough energy to get past. Remember, these guys are surrounded by negatives. The electrons are on the outside, so they're surrounded by negatives. They're going to really want to repel. They don't want to be near each other, unless there's other sorts of intermolecular forces of attraction. So you need them to collide. They have to collide in order to react. That's why we keep sodium away from water. That's why we store it in mineral oil, so that it doesn't come in contact with water, therefore we won't have any sort of explosion. Okay? So you need to have effective collisions in order for a reaction to happen. How can you speed up a reaction? You can increase the temperature. That's the same as adding kinetic energy. Okay? Adding heat is thermal energy. Those are different types of energy. Kinetic or thermal energy. If they are moving faster, this means they're moving faster. That means they're going to run into each other more. I always give you the example of if I have you run around the gym versus if I have you walk around the gym, how are you going to, when will you have the most chance of running into somebody? If you're running, the faster you move, the more collisions, and the more energy, which means they're more effective, okay? Add a catalyst. This lowers your activation energy, which makes it easier. You have to have a less effective collision if you have a catalyst. It will help bring them together. If you dissolve them, you form solutions. All right, solids mixed together. You can certainly get powdered solids mixed together, but it will work better in a solution. So we'll say solutions. The more particles dissolved, the better. So an ionic one, which is going to give you more particles, is going to dissolve better, is going to not necessarily dissolve better, but will react faster. Additionally, increasing surface area gives you more area for collisions, okay? And in the case of a gas only, increasing the pressure will force them to, which means a smaller volume, which equals more collisions. Those are how you want to speed up reactions, how you get to make more effective collisions. Let's talk about a potential energy diagram, okay? I'm going to talk about two of them, exo and endothermic. You always have energy on the y-axis, and your x-axis is reaction coordinate. It could be time. All of these potential energy diagrams have two platforms. I call them platforms because they're kind of starting and ending points. Excuse me, this one is backwards. Starting and ending points. Your reactants and your products. We generally look at reactions as a black box. What that means is we have A and B turning into C and D. We do not care about what happens in the middle. We don't know. We don't focus on the mechanism of the actual reaction. You won't do that until college, maybe AP Chem, but A and B we snap our fingers and all of a sudden it's C and D. These diagrams are the closest we come to looking at the difference between reactants and products, okay? This one right here, they always go up first and then they come down a little bit. You always get some of that energy back. This is your endothermic reaction. This is your exothermic reaction. Exothermic is a step down. Endothermic is a step up. Endothermic, your products have more energy than your reactants. Exothermic, your reactants have more energy than your products. So exothermic reactions are generally more spontaneous because you're trying to get to as low energy as possible. All right, what do you need to know about these diagrams? You need to know that the top point is the activated complex. AC is activated complex. That's the highest energy. That's what happens when A runs into B. It's a high energy that only lasts for a tiny little fraction of a second, okay? Activation energy is how much energy you give to the reactants to get to the top of the activated complex. You start at the platform and you go to the activated complex. That's activation energy. Start at the platform all the way up to the activated complex. It should be obvious from these two diagrams that an exothermic reaction has much less activation energy than an endothermic reaction. Endothermic reactions energy goes in. Okay, you have to put in a lot more energy. So this is the activation energy. Activation energy. Also, please know that these are reversible reactions, okay? We talked about that in this unit, equilibrium. We can go backwards. Since they're reversible, there's an activation energy for the reverse reaction. That's from the platform of the products up to the top of the activated complex. Platform of the products to the top of the activated complex, okay? So the reverse reaction for an exothermic is much greater than the reverse reaction for an endothermic. If you can take a step back and look at this, you can see that an endothermic reverse reaction becomes exothermic. It should make sense that way. They're just backwards. Okay? Also, what you need to know about these diagrams is delta H. Delta H is on table I. Delta H is the heat of reaction. Delta H does not change. It's the same for this reaction under the given conditions. It is always between the platforms of the products and the platforms of the reactants. There's your delta H in both of these cases. It's heat of reaction. It's the energy of the products, product energy, minus the reactant energy. Okay? The same thing over here. That's why delta H is negative for an exothermic reaction and positive for an endothermic reaction. Okay? The total potential energy of any of these phases, any of these states, okay, is always starts from 0. Okay, so it would be from here to there, here to here. I will put the arrowheads in so that it's clear, and here to here. So this is the energy of the reactants, the energy of the products, and the energy of the activated complex. The activated complex is the highest energy state in one of these diagrams. Okay? They'll usually ask you to put some things together. They might give you the activation energy of the reverse reaction, and they might give you delta H and ask you what the activation energy of the forward reaction is. Just do a little bit of math, okay? Just do a little bit of math and you can figure out that it's the difference between the two. That, I think, is about it.